Hello guys, in this video I will be talking about Verilog and how to design in Verilog. And I should mention before we start that Verilog is actually called Verilog HDL. We just usually call it just simply Verilog to shorten it. But since we call it normally Verilog HDL, there is also another language called VHDL, but VHDL is not the same as Verilog HDL. They are two different languages entirely, and they both have different advantages in different aspects. However, we will not be using VHDL in the labs. We will just be working on Verilog HDL, working with Verilog HDL, and the HDL actually stands for Hardware Description Language. Just remember that, maybe it will come up, but I'm not sure it will. But it's important because this acronym is basically telling you that this language is not a software language. It's just a hardware description language, and just basically by writing some lines, you are actually technically designing circuitry. However, this circuitry is not generally visible to the naked eye per se, because it's much smaller than a, say, something you might find in Tetrises. And I think you know about those circuit boards. Let me show you Tetris board. For example, if we have an example of it before we go on. So basically, and these are very old technologies, by the way. These are not the current ones. However, this is basically a few centimeters long each from each side, and in Verilog you're not designing something like this. You're actually designing something like this, however in a very tiny scale. You're basically designing something in these, but again even smaller than these. And these chips are like about 3 centimeters each long and maybe 1 centimeter thick, and 1 centimeter wide. And you're designing something even tinier than this in Verilog, and at least in these labs it may be larger when you go on to more detail in it. Okay, maybe we can start with some code schemes. And okay, the first example that I have right here is just ignore this part for now. I'm just going to go on to that later on. I just put some lines here to separate them. And if you have a look at here right now, maybe I can also actually just, okay, so to not get you more confused. And I mean, consider this just a file of its own. You're supposed to actually save them in some other file, generally mostly. But then again, you can also, I'm getting ahead, but I'm just explaining some stuff ahead of time. You can actually design your modules in the same file as well. This would be the top module of your project in Xilinx ASE, and this would be some other file that needs to be added to that project as well. And you can have that in the same file as the top module, and in the same, you can basically have this in a file and this one and this other one in a file as well. I mean, maybe like 3 files, 2 files, just 1 file. You can do any combination of the two as long as they are separated by the keywords, basically. But I'm just going to be showing you how we would write a top module. We have different methods to have top modules. If your design gets more complicated, we would suggest you to have multiple designs in other files, or again other modules like defined in the same file but below the main module. And just basically by doing that, you're separating the jobs to other instances, and then your whole instance, your whole instances make the whole design work by working with each other basically. And in this example, I just have written these signals that we would connect to a board, like a clock signal and RST signal, LEDs, buttons. Um, Let me see. And these are clock RST, which is just reset, and buttons are just generally inputs. And also, again, switches are also inputs. But LEDs and 7 segments and some other GPIO pins are generally outputs. Also, GPIOs can be inputs as well, because GPIO stands for general purpose input output. Let me write it if my voice doesn't get correctly recorded. Input. But then again, also sometimes people prefer to write IO like this, but it's also fine to write like this as well, but mostly like this. And when we have a GPIO, we just can define it as an input or an output. It doesn't matter. You need to choose it according to your need. Um, but anyway, maybe I can get back to the module. And by the way, I have written these input and output keywords to indicate which signals should be inputs and which signals should be outputs. And you can see here that I have a wire. However, in the lab you have regs, and I'm going to talk about it in a bit again to let you know what it is, how they work, how they are. I have another example that I can show you. And again, if these signals are 1 bit, you can actually technically do it like this, 0 0. But I mean, since it's just 1 bit, you can do just clock and reset. You can also again just have 1, and then you can also have input RST as well. These work the same way, and I mean, just by having a comma there, you can just shorten a few lines as well. And if you have multiple bits of these signals, for example, these buttons, we have 4 buttons, and since we have 4 buttons, we need to write 3 and 0 here. I'm not sure if it's visible in that way. Maybe I can change it to another language so it might be visible. Let me see. Maybe Java. I don't think it's changing. Maybe Python. Okay, maybe a little bit more visible. Since we have 3 to 0 here, it's basically like 3 to 1 and 0. So we have 4 different buttons. And again here we have 7 to 0, which should be 8 different LEDs. I'm not going to write 7 to 0 here, but it's 8. And then, like I said, we have 2 different methods of writing top modules. Mostly we can have instances defined like this, or we can also actually have always blocks. Maybe I can change the language again to Verilog so it shows up more correctly. We can have always blocks, and also we can combine the two technically, but if you are separating your jobs, maybe this is a better way of doing it. However, technically you could have, for example, let me copy this one. You could technically have, again here, this one as well, and this would work in the same way as it would in here as well. I mean, they would be the same basically. Um, okay, you can see that these are the module names. For example, if I had another module which would be button decoder, I would write it like this, and again, these signals would be clock, ISD, buttons. I can actually rename them in other ways as well. I'm just going to name them differently this time. Maybe like this, make it clock. And don't forget this semicolon here as well. It's necessary, otherwise you will get an error. And let's see, this would be an input clock and also reset. And our data in is this button right here. So since we have 4 bits here, we would say input 3 to 0 buttons, and again output. You could have a reg or a wire here. I'm just going to put in the reg. I'm not going to design the rest of the thing. I'm just showing the inputs and outputs. And our data out is connected to this button to the LED, which is just 8 bits. So I'm just going to write 720 data out. And you would have your design here, which could be another few instances, a couple of more instances, or you could have assigns, or you could have always blocks. Again, I'm gonna go into more detail in the next example. And this would be your module name, and this would be your instance name in this file. Basically, in Java, maybe you're more familiar with it. If you had a main function in Java or in C as well, if you needed to create an instance, a variable, you would have, for example, a string. Maybe in Java it would be something like this, string, and maybe like Istanbul. This would be how you would do it, and this would be your object name, and this would be your variable name, and it's pretty much like this. And this would be your module name, and this would be your instance name, object name, instance name, uh, no, variable name, instance name, object name, module name. And again, if you had some other object that you had designed, maybe, I don't know, bank, for example, in Java, normally you would have a class bank, and you would design your class object after this one as well. And I mean, since you need to design a bank class right here, it's basically like this. So I hope this is more easy to understand how to write which one you need to write here. You can have multiples of this button decoder as well. Basically, let me show you like this. You would have instance 2 maybe, or you could name it something else entirely. You could name Ahmed and work with that, but I mean, name it properly so you can work better, work easily. Um, Let me see, let me delete these ones, and let me also delete this one as well. And again, you need to, if you're having an output here, you need to choose different names as well right here. But let me delete that, and let me see. Okay, I'm gonna talk about reg and wire in a bit in the next part. And okay, you can also actually see that these instances have signals which are defined very differently from each other. and you can use one of the other two. However, you cannot mix these two. So just have it like this or like this. And in the exam, we might ask you to do it one way or the other. So just be prepared, and it will be given to you in the question if we needed you to define it like one of the ways. And by the way, let me actually go back and show you. Okay, I might have different names here, but these names are my signals in this module. However, in this module, in this um, design, these names are important. I can't write buttons. No, maybe. Okay. Might have mistaken it right here. It should be like this. In this module, I need to be working with these names, these signals. However, in here, I need to work with these ones. So don't confuse the two. They are different from each other. And again, as you can see here, we have multiple different names here. They can get a little bit confusing sometimes. And let me just show you how it should technically be. And you can actually basically understand because you're using clock in this module. So you know that the signal in the parentheses is the top module one. And these ones are generally the LED controller module signals. And let me show you simply LED controller, and I would have the signals right here. I'm gonna write it in a second. And module. And I'm not gonna write the inside of it, input and output and whatever whatnot. And you can see that our clock in is a signal that we need to input or output. And our reset system is like this, and data in would be this, and data out would be like this. Again, you're going to be working with these signals in this module. However, in this module, you're going to be dealing with these ones. We might need you to write these instances in either way, but we will specify which one. I think that's done for this example. We can move on to the next part. Okay, before I go on to this other part, I should also explain to you that I just mentioned that we would require you guys to write these in either way sometimes, and we would specify which way you need to write it. And we would basically most likely say list or by name, not order. And I just realized also that I need to also mention how these signals should be listed, by the way. And list parts by name would be basically like this, and these names should be used. That means that. And order means this one. And order would be like, you can't just have reset before clock because in your module design, which is decoder, let me see. If I have designed it like RST buttons, let me do that again. I'm just naming them the same way. And you know that I named this like data in, data out. I'm just showing you for now. And if you have designed it like this, you cannot just change these ones because if it sees a name before a comma right here, it assumes this is connected to this one. And this is going to be connected to this one, and this will be connected to this one, and this one to this one. So if you change these names, it will not work. If you do it properly, like you have to, it will work like this. However, in this name version, list parts by name version, basically, you can change the order, basically like this, for example. And you can again just copy this one and then let's get this one here, and it will again work. It doesn't matter, even though you have this order right here, it will still work since you've connected the ports by name, which is pretty important to design your modules. And I think after this I can go on with the other part. Maybe also I can just write order is important, and maybe names are important. So if you're just taking screenshots, you can maybe take it like this, so it will be easier for you. And if I go on to the next part, let me see. Okay, in this part, I've just copied the rotating dot file which we have in lab 5, part 1. And let me show you the full thing. Maybe I can also actually shorten some of these because you don't need to see them until I'm explaining you what they are. And also, by the way, you can see this output wire and wire. You can have output reg and output wire and wire as well. And this one is wire because this LED signal is coming out of this instance. When this signal is controlled by an instance, it should be a wire in the top module. In your other encapsulating modules, and this top module is encapsulating these two modules. So this LED signal has to be a wire because this is controlled by the LEDs are controlled by this instance. And again, this LED is again written as wire because the instance is controlled by this one. I just basically mentioned this one as output in this design, but I didn't design it right now for this example. And this button instance is outputted from this design to this design, and this takes it as an input basically. That's why this is just saved as a wire. And again, if you have just 1-bit wire, you don't actually need to write it like this explicitly. You can just have it like this, and if this was just 1-bit, this would still work. However, it is still a good practice to have written this, even though it is just 1-bit. It's good practice to write it like this, because if you need to increase the number of bits on this signal after some time, you're not going to forget to write the wire. But if you increase the bit size in these instances, you may forget to increase the bit size in the top module, so your module will not work again. So just have those written because it will work better for you. And moving on to this part, I just have this design completely written as is and just added a few more lines that I'm going to mention. And you can see that we have a few regs, a few inputs and outputs, and a parameter. You're not going to use parameters in the labs if we haven't defined them. You don't need to define them in the labs. We have assigns, we have always at posage blocks. And I mentioned that you can either have instances or you can have always blocks. And we generally have two always blocks, which is one of them is always at posage clock block, and the other is always at star block. You can also just delete the parentheses here and just have it like this. I personally just prefer it with parentheses. It's just a separation thing. And let me see, let me just close that one to make it easier for you. Just ignore these comments for now. I'm gonna go into detail about them. And also, before going into these ones, we have this assign one, and this assign is, I just added this wire here, and this has to be a wire. This cannot be a reg. And again, ignore this one. I'm gonna tell you what it is afterwards. Uh, this one needs to be a wire because assign can only assign to wires, and if this was a reg, and if you were to synthesize this code, it would give an error like assign cannot be used for reg or something like that. I don't remember the exact error, but it will not synthesize. And again, since this is just one bit, you don't need to actually write it explicitly. However, it is a good practice. And again, this is just a few simple simple codes, and you could basically have something like this as well. And this is just an if statement, and I think you already know what this is. If RST is 1, the result, this data should be the same as this value. If this is like 1, temp flag will be 1. And if RST is 0, the result would be this one. The temp flag would be this one. And I just randomly wrote these signals and wrote these random bits as well. It doesn't really matter. I just coded it randomly to show you how it works. And this whole line is technically like an always at star block. It acts exactly like this one. However, it's just one line, and if it has just a wire. However, if you were to do it with a reg instead of a wire, and with an always at star block, you could also technically do it like this. And let me comment this one out as well to show you easily. Okay, let me also uncomment this one. And you will define your variable as reg, and again, you can have multiple bits like this, but I mean, this example just has the 1 bit one. And this whole thing is basically this. And again, you could actually also just separation. You could have temp flag, RSD, question mark, date out, counter 12. You could just have this line, or you could also have these lines as well. I mean, either way is fine. I'm gonna comment this out as well. And these are just the same things. And this one is the same thing as this one as well. And you can use it either way. But I mean, this might get a little confusing for you guys sometimes. However, if it seems easier for you, you can use it. But you can't use it for regs. You can only use it for wires. And for complex computation ones, you can just write it like this. It would be difficult for you. So maybe you would want to use always at star blocks, which will be much easier. And let me go on from this one. I talked about this. I'm gonna talk about this always at posage clock part now. Am I recording? Yeah, I am. I'm recording. I was just checking. In always at posage clock blocks, and you would have your clock signal here always, unless otherwise restated. You just have these one-liners and nothing else, nothing. You can't have anything else here. You can't have any ifs, any switch cases, any other code blocks. You just have these one-liners. This is a writing methodology of Fatih Hoca, design rules of Fatih Hoca, and you need to follow these guidelines, follow these design rules, because we're going to be grading you on that. And also just be careful about the indentations and how I do it. Again, you can also actually have it like this. I would generally prefer it like that, but this is also fine. But be careful about the indentation, and I mentioned in lab 1 and lab 2 as the rules. You need to be careful about how your code looks. You can't have ugly looking code as well. And if you need to, you can comment like this is the max value for count, for example. You can write simple commands as well. Okay, and also in this always at postage clock block, like I mentioned, you can't have anything like this. Never have something like this. Whatever you do, never have something like this. This is the simplest design rule that you will know about. And generally don't delete these ones. These are for simulation in Xilinx, in the iSim simulator, but I mean, just leave these as is. And these should be left as is in this block, and do not use these in this always at star block as well. Don't confuse these ones. You need to be using this one in this block. And by the way, I should maybe mention that these ones technically, this line and this line technically is running parallel to each other, running at the same time technically. But since it's not a software, it's not actually running parallel. It's just circuits, and they happen to work at the same time. And for software people, we basically say it like that. These lines are running parallelly, and I think these are called. If I can, let me see if I can remember the name for it. I can't remember. Uh, Non-blocking assignment. Okay. These are called the non-blocking assignment operators. And by non-blocking, it means if you're running this code, and since this is non-blocking, you can at the same time run this line of code. That's why we call these non-blocking assignments, and these are blocking assignments. This needs to be done, and afterwards this would be done. However, it would still be pretty much at the same time. You wouldn't be able to differentiate them. And this is not an important name thing. You don't need to remember these names. I'm just mentioning them. They are technically called non-blocking and blocking, and they don't matter at all to your designs. Just have it like this, and never have this again. I can't tell it enough. And in your always at star block, you just always have your own design. You just design your stuff in here all the time. And let me see. Okay, you can actually have multiples of these blocks. You can basically have an always posage clock. I'm also writing begin and end all the time, but if it's like just one line, for example, tab flag, next, for example, if it was like this, you don't really need to have this begin and end. However, it is still a good practice, because otherwise, if you're working on your design, if you need one more line, you're gonna forget this one, and your design will give an error. So writing like this is mostly easier. And again, since you can have multiples of these blocks, you can also have multiples of this one. And as I demonstrated here, we have one, and we have another one here. And again, if you're driving counter here, and by driving I mean assigning some value to this counter variable, you can just have counter 0, for example. This will cause a multiple driver error. It's called a multiple driver error. Let me show you what it's meant to be. And this will not synthesize, and sometimes in other design environments which work with Verilog can just give as a warning, not as an error, but it should be treated as an error. They are faulty, they do not work, and you cannot have this line. This would cause multiple driver. And again, if you're having counter here, you cannot drive it like 5 or 4, and this would still cause a multiple driver error, even though these are different blocks at all, they don't matter. If you're driving the same signal in the same module, it will be multiple driver. It will be a multiple driver error. And again, also, if you're driving data out next year, you cannot drive data out next year, and you cannot drive data out next year again. You can't do it in multiple blocks. You cannot drive it. However, you can technically have something like data out, or you can do this basically, since you're not you're assigning the value here. However, you're checking what value it is. You're not assigning something here, so this will not cause a multiple driver issue. This will be fine. And generally, we don't use data out next year, and it's much easier to have the data out signal itself. It's better to do it that way. And I might forget, but I can also mention how it should be, how you could use that. Maybe I can actually try and mention that. Okay, for example, consider that we don't have this code right here. It's just command, but it's not there. If you had counter next here and you didn't have any other problems, that these are not faulty, so they are fine. Let me actually delete this one since we don't need it. If you had counter next here, this block would need to know what counter next value is. However, right here, we don't know what this value is, so this will likely cause some warning to you, and you cannot use it like this. It wouldn't be the good practice, so generally using counter will be better. However, right here, if I were to use a counter next equals to 5, for example, I would be able to use it, and I could actually assign some other value to it as well. I can do data out next. I'm just assigning random numbers as an example. And you can do it like this here because you just gave a value to it right here. And otherwise you shouldn't be doing it like this. You should be just checking counter as well. And again, there is also one other way that enables you to have counter next here, which is basically this. Let me unblock that command, uncomment that block. And if you had this, for example, or even this as well, I'm just going to leave it like this. Since you're assigning some value to this counter next, you are able to write it like this. Otherwise, it would probably cause issues in the long run. So if you don't have this one, you don't do it like this. And I'm gonna get that because that's a way better approach. And again, if you didn't have this line, these lines of code right here, and since in these if conditions and else if conditions and else condition, we have completed these signals and assigned values to each of the two signals here. This is fine. This is a good code. This is a working code. However, if I didn't have these lines, or just this line, or maybe like this would cause latches, what we call a latch. And what do we call that? Um, you can consider it like basically like in a very higher level, higher language level, like person A tells person B to go get tomato X if the store has X. I'm sorry for basically the robot voice, but I'm just writing. So if person A tells person B to go get tomatoes and eggs if the store has eggs, then what will happen is if the store has eggs, in that case, maybe I can write person B gets tomatoes and eggs. In this condition, person B knows what to do. However, if the store has no eggs, then person B is confused. The person B doesn't know what to do. They can't choose, and they may just, since the store doesn't have eggs, they may just get the tomatoes. But I mean, if the person A is cooking something with both of these ingredients, this just tomatoes will not be useful at all. So person B doesn't know what to do because this person is being controlled by person A here. And in our design instance, person A is you and person B is the design. If you're not telling the design what to do in every case, then the design doesn't know what to do. And basically it would be like this. If store X, X, and else, normally you would maybe perhaps get tomatoes maybe, but since you're not explicitly saying to get tomatoes if the store doesn't have eggs, you're basically just writing these two lines of code, which doesn't work for hardware design. This would be faulty. To get rid of that, we just have a default value to it, like get tomato or get maybe cucumbers. And if you do it like this, then it will not cause batches. Or again, you might actually have as and cucumbers and not have anything here at all. However, it's still technically a good practice to get it. Still a good practice to write get cucumbers at the top. And in our design, basically, I'm gonna delete these two lines. If I didn't have, for example, these, and I didn't have these, and I didn't again have these ones, this wouldn't know what to do when this value isn't one and this condition isn't one. Data out next and counter next wouldn't be decided by the design, so it would be left hanging. It wouldn't be a good design. And to get rid of that, if you're not going to write this else part that I just have here, you can have these. If you have this, it will still work. It will not cause a latch. And again, it's basically the same thing. Since RST is going to be 1, it will still assign this value to data out next and this value to counter next. And this will not matter if RST is 1 and if this condition is met. This is basically the else begin part. And writing these lines would be a good practice for you guys. Just don't forget to write it, it's way better. And I talked about latches. And maybe I can also show you what a latch looks like for a in schematics. I actually have driven it in Paint in the lecture, in the lab session, but I'm gonna draw it again. It would be something like this. Let me see. If I had some 1-bit values, for example, I'm just drawing it very crudely. Let me see. Okay, this would technically be a multiplexer, and let me write the name as well. And this would be our enable line, and if this line, hold on, if the value in this line is 1, then this wire gets connected like this, and the output would be this value. However, if this value is just 0, then this line gets connected and the output is equal to this one. And for example, if you had person A saying işte go get egg, tomatoes and eggs if the store has eggs, and if the store has eggs is this enable line. If store has eggs, it would be 1, and tomatoes and eggs would be here, and the person would be getting tomatoes and eggs. However, I can actually maybe write that as well. If the store has eggs, the person B would get tomatoes and eggs. However, if the store doesn't have eggs, the person B wouldn't know what to do, so we would be drawing it like this. You can actually also leave it like this, but it's a better practice to draw it like this. And this would be a latch. This is how we would draw a latch generally, and this wouldn't cause a latch. And this is basically what we do right here. And this is what we call data out next generally. And this is what we call data out. So if I am coding in Verilog, you can see that always at posH clock, data out next is basically like this part, data out next. And again, I should actually have this clock right here. And again, this tool. This one is a multiplexer, and this tool is called a flop. Let me also write it like this. This part would be a flop, and in this one, if we had, for example, just delete some of these since we don't need them. Okay. Maybe if we had RST and 0, if RST is going to be 1, this data out next is assigned 0, or maybe counter next. Consider this as counter next. If RST is 1, counter next is going to be 0, but otherwise, if RST is 0, counter next will be counter, which is basically this line. That's how it basically works, and I can actually write the code easily right here. RST t counter next is 0, else counter next is counter. Or again, also I could just delete these two lines and counter next is. This is even a better way of writing it. And again, I didn't write begin analysis since this is just a one line code. However, it's a better practice to write begin and end. And also indenting properly is important. And I would also actually need my always at posage clock counter. Basically, this part is this whole drawing. And again, I can't just have these because these are driven here. So this will cause a multiple latch, multiple driver, and this will also cause a multiple driver as well. So I cannot have these here for design purpose. And I talked about this. We have also multiple clock errors, which are the most common ones. And you need to do your designs with a single clock. And in this lab, we are designing a single clock. And this clock has to be a free running clock, a physical clock, which is coming from outside the FPGA, or coming from a DCM, which is a digital clock manager inside the FPGA. And otherwise, if you really need to have multiple clock domains, you need to consult an expert on it, such as Fatih Hoca. And that is because the timing problems caused by multiple clocks cannot be detected in simulation. For example, if you have two clocks, one of them could be 300 megahertz and the other could be 100 megahertz, you will have issues with the design because some signals are going to come faster and you are going to lose those samples, lose the values in those signals, and your design will not work properly. And even, I mean, I just mentioned two clocks, one of them with 100 megahertz and the other with 300 megahertz, but you might have two clocks with each with 100 megahertz. However, physically, the physical clocks are not technically completely 100 megahertz. They are generally something like 99999 megahertz or 995, 996 megahertz, or sometimes even 100,004 megahertz as well. So if you have 200 megahertz clock, it's going to probably be something like these two. They are most likely not going to match exactly, so it will cause timing problems. It will be difficult to work with, and if you don't need to work with two signal clocks, don't work with two clocks. Just work with one clock at all times. And also, let me see. Also, multiple drivers can be found in module instances as well. If I had something like data to button to LED, and this was an output, and since this would be also an output, you wouldn't be able to use this because this is still technically a multiple driver error. This module is trying to drive this signal. However, this module is also trying to drive this signal as well, so it doesn't work. I mentioned this multiple clock problem. There's also this not creating a flip-flop problem. You might have not created a flip-flop where you need to, and let me just read this part here. If we assign a value to a variable in a clock cycle and use that variable in a different clock cycle, like here, we're assigning some value to this data out. Consider this like this, for example. However, in the next cycle, I'm going to need this value, the previous cycle's value, right here. So I cannot do it like this. So I need a flip-flop, which is just this, and basically using these. And that's why we need to have that variable in a register, which is a multi-bit flip-flop. And when we declare a variable as reg, that does not mean we are storing that variable in a register. Reg is not a register. I mean, if you just had this reg tab like this would not be a register. You need to have these as well. To create a flop, we would have this block here. We would have these. This is the most important part for it. And var would be the flop output, like I have driven here. And the next one would be the flop input. And you can sometimes just write nxt and sometimes write next. It doesn't matter which one you like to write. Just be consistent with it though. Don't just have nxt and next in the same module or in the same design. And after using it like this, inside your always at star, you need to have at the top this line, like I mentioned here, and then you need to again design your code in this way. On the left side, you would have the next version, next signal. On the right side, you could have some other variable that is not next or something else entirely. And you could use just 5, for example, here. It would be the same, but you can't use data out next for this would be an issue. Yeah, just like I mentioned, this is the same thing. And I think that's about it for the examples. Okay, and just like I mentioned in this part, we have these simple drawings. However, I just did this in a rush, so these are way better drawings of the designs. And as you can see, these are flops, and these are our always or assign blocks as well. These are just one-liner blocks, and these are the star blocks, always the star ones. And these are technically the always at the lines in always at postage clock. And you can see here count next, which is this one, previous button, which is this one, and this assign part is this one, which is button and not previous button. And there is some sort of an inverter in here, and then there's also an AND gate here that connects the two, and then assigns postage button. And in this always at star, we're using postage button, so we just connected this one, and we're assigning value to count next, which should be here, and we're using count to calculate this count next, which should go back to here. And this would be how you would draw your schematic if you needed to draw one. And you can see here, let me see, we have this count, and okay, I was missing the reg part in this part. And also I forgot to mention, you can just do output 3 to 0 count and then just have reg 3 to 0 count as well. This is the same as output reg 3 to 0 count, but it's in 2 lines. You can write it either way, and you can see this wire here, and you need this assigned as a wire to be able to use this assign block. And even though this is a wire, you can use this to check a condition, but let me see, but you cannot use wires on the left side in always at star blocks. You can actually use it on the right side, like here you could use posage buttons. And I think that's pretty much it for this part. Let me see, is this different? I think this is mostly the same, and let me go through each one. Yes, instead of assign, they changed it to reg here, the posage button one. And let me see, I think I mentioned most of these. And by the way, these codes we call RTL code, which is written like here, and RTL stands for register transfer. And maybe just try to remember this as well. It might be important in some way. It's actually important in our designs. And these RTL designs break your algorithm into clock cycles. And yes, I think it's pretty much explanatory. You can maybe read them up by stopping the video if you want. And we have this stub module, and we have these instances and these modules. We call these sub modules. And in these modules as well, you can have more sub modules. You could call some other module entirely, and those would be called basically sub modules. But otherwise, you can just call it a module. And let me see. Think of it as a state machine. Yeah, think of these codes as state machine. Like in this state, these signals would be these values. This is basically pretty much like it. We don't have, for example, like state here as well, and maybe this is 3 bits. We could have these, and also we could check if state is some value and do it like that. But for this simple design, we don't need it, but it's technically there, even though you don't recognize it as easily. Store everything that needs to be remembered between cycles. Yeah, like I mentioned, we have registers, we have flip-flops to store variables. State in a, okay, just like I mentioned, state next would be a register. The case, you can use case to write your code easily. We could have, for example, if we had state next, we could have case state, and then 0, maybe also begin, and we just write all of these, and we would have this add case here as well. And generally you can have the indentations like these, but you need to go in one right here and also here. And if these are just one lines, you don't have to actually write it like this. You can just write your code right here. And you can have the indentations like this, like I said. However, you might also want to just write it like this to not confuse you further. And this state variable, if the state is 0, you will do this part. And then if the state is 1, you will do this part, and if it's 2, this part and this part. And in the example I just showed you, it was like 3 bits, state and next. And I'm not writing state next here, but consider I have written it already. And since we have 3 bits, it goes from 0 to 7, the decimal values of it. And if I'm not designing anything for the other values, for example, I could not also design anything for 2. I could have a default keyword right here and have it like this and write my default code right here. This is basically like else part as well. These are how they work basically. You could also have technically here, for example, RST and then counter like this. This would technically still work, but you need to be careful about the decimal values of this one because this will be the leftmost value, and counter is 22 bits, so this would be 23 bits, and this will be a lot of cases. And if you don't need to do it like this, don't do it. It's not exactly the best practice, and we don't generally write it like this. We just always have it like this. It's way better to do it that way. And I think that's about it for the case state. Let's see. Okay, these coding style is technically a basic truth table. You would be assigning these ones and zeros to these signals, each bits in these signals. Outputs depend only on inputs, and in this block, for example, the inputs are reset, counter, data out. The right side signals and these conditions would be the inputs, and the outputs would be these signals. And these outputs depend on these condition signals and these signals. And I think that's about it for this slide. Okay, the golden rules, the most important rules, like I have mentioned before, you can't have it like this. If you had in between here count next equals count, it would be fine, but don't do it like this. Just if count next something else is better, don't do it like that ever. Let me see. This would be better, but if you didn't have the flip-flop, it's not still done. And let me see. Okay, this is again not done because this creates latch, and because you didn't explicitly define an else or something here. And this is still not working because you're using the same signal. You're not supposed to use count next on this side. And the best way would be something like this. This is how you should do it. And I've demonstrated here. We're using the variables without the next values, next string, but we're using next ones here. That's basically how that should work. And always have default assignments. These lines is what we call default assignments. This is the best practice you could have in designing. And no indirect combinational loops. Maybe if we have some sort of an example, this code, can I copy it? Let me see. Okay, if we have this code and then we had, for for example, this is still a combinational loop, but it's an indirect combinational loop, which has two different always star blocks, but they are connected to each other. And when this value changes in this block, this value, this block is then technically run. I mean, these are different stuff, so they are not technically run. But if the signal changes, then these these are changed. So these values change, and then again these values change. So it's a complete loop over and over again. So you cannot do it like this. And having your whole code in a single always code is the best practice. It's easy to see, it's easy to understand your code. If you really need to do it, you can do it, but you don't do it. Avoid it as much as you can. Just having one single always block is better. Single always at star block is better. And multiple drivers, extra input may be needed. I don't think I need to mention this exactly. If you need to assign a variable through these to always star blocks, you need to have some sort of a arbiter, which is a decider, basically, someone who decides what the result should be through the arguments, and you may need some extra inputs to decide as well, but this arbiter would be deciding which one the variable should choose to be. Okay, these clock signals are the same clocks. They're not different. You could also technically have you could also connect them like this and write clock here maybe. But just writing clock and clock here would denote they are the same variables. They are the same signals, not variables. And don't use multiple clocks like I've said. And do not ignore warning messages other than what we mentioned in the other video as well. And we can tell you what to ignore if we need to, if we have other warnings that will come up other than the ones for number ones. This is the warning which is delay. Because of this little thing, this warning comes up on Xilinx, which is this part right here. Don't delete this, like I said. This just causes this warning, but it's not important. They are not used for the synthesis, like it says. And a couple of RTL clarifications. How to interpret. In these always blocks, the variable wouldn't be 5 and then 3 during this time. Throughout the time, it wouldn't be 5, it would always be 3. What's at the bottom is the variable. And if you had something like this, now just like it says, what is important is the and line. If the flag is 2, the variable will always be 3. But if the flag is not 2, the variable will then be 5. It's like this. And let's see what is missing on the left. Oh, it just says else begin and then does it like this. And it's mostly the better way of writing it, because if the RST is 1 and the flag is also 1, what will happen here is variable 2 will not be this value, but it will be this value if both of these are 1. But what we want is for reset to be the mostly chosen signal, preferred signal. If RST is 1, this shouldn't be the signal that we get. This shouldn't be the result that we get. So we write it like this. So if RST is 1, this part is never executed at all. So that's a better way of writing it. Just have this if RST and then else begin and write your code inside there. Previous, okay, these are sample clock and samplings, previous sample and current sample, and you can check for posage of a single signal using these samplings basically, and like we have in the first slide, I think it's made possible using these. This flip-flop samples the button signal and has the previous button value here, and if the previous value is 0, which has this NOT gate here, and the button is 1, then we will have a posage, and you can see the waveform here. If the previous sample is 0, okay, maybe I can actually copy this variable, copy this line to show it better. Okay, let's see. Okay, if the previous value is 0, as you can see right here, and the button is current value is 1, we got a posage. That's what this basically is. And you can see here the previous sample of the signal, the current sample of the signal. Or you can treat it like the current sample of the signal and the next sample of the signal as well, like I have written here. And I think that's it. Note that you may mix instantiations and behavior. Like I said, you could have some modules and then have always at star blocks as well, or assigned blocks. In most companies, it's a coding guideline not to mix them, so it's better to have instantiations or your always blocks. It's better to choose one way. It's cleaner, and I think that's about it. So we will see you in other videos.